Awesome. Welcome everybody to our new AI for Science talk. So for those of you who don't know me, I'm Raj, one of the co-founders of AlphaKive. And here we help create tools to help you keep up with and apply the latest research. So one of the things we are also very passionate about is our community talks. So today we are very passionate and excited to have Akshay Agrawal, who he was a TensorFlow contributor at Google Brain, PhD at Stanford, and now working at Marimo, actually CEO of Marimo. So AlphaKive and Marimo are actually doing a lot of collaborations now, so where they're helping us provide implementations for papers. So yeah, very excited to have Akshay, and I'll go ahead and pass over the mic.
Thanks, Raj. And thanks everyone for tuning in from all over the world at all time zones. Really appreciate it. Um, so this talk is about minimum distortion embedding, which is a framework and algorithm that I developed during my PhD at Stanford, that generalizes over 100 years of embedding methods. But at the same time, it's more broadly about the tools that we use to do research. So how the tools we use shape the way that we think and ultimately the quality of the research that we produce. And it might be surprising to some of you, in fact, it was surprising to me, that after finishing a PhD in convex and non-convex optimization, I decided to develop a new kind of Python notebook called Marimo. But I promise there is a connection, and I'll try to sort of motivate that in this talk. And to understand that connection and sort of this is the broader theme of this talk, it might help to understand a little bit about my background before we dive into the main topic, the math, and the research framework. So let me share my screen.
While Akshay is doing that, just a reminder, if you haven't joined one of these before, please leave your questions in the Zoom Q&A section. And you can, I'll go ahead and be monitoring that. We'll have a pause in the middle, but plenty of time after the talk.
Cool. Second. Okay, so a bit about my background. So as Raj said, my first job out of college, this was in 2017, was at Google Brain. Back when Google Brain actually existed. I'm not sure how many of you guys followed deep learning research back then, but today Google Brain has been absorbed into DeepMind. Google Brain was a totally magical place, by the way. It was like paradise for researchers. Like researchers had so much freedom to follow their North Star. And I actually don't know if research labs like that exist anymore today, at least in industry. But anyway, at the time, I wasn't a researcher, but I was a software engineer. And I worked on TensorFlow, specifically TensorFlow 2, before it was released. And funnily enough, my job was actually to make TensorFlow more like PyTorch. Um, and for those of you who are fortunate enough to have started your deep learning journey with PyTorch, you may not know that TensorFlow was not an imperative framework, but actually required you to wire up a static data flow graph before you ran any code. And as you might imagine, it turned out this was really painful for researchers, and it really limited the kinds of research you could do. And in particular, it made things like reinforcement learning with dynamic control flow kind of hard to do. And so that's why PyTorch was so successful when it burst out onto the scene. Um, it just made it really easy for researchers to express themselves and allowed them to sort of tackle new kinds of problems that previously tools like TensorFlow kind of prevented them from exploring easily. And so this was the first time in my career where I really viscerally felt how the tools we use shape the research that we do. And so that was back in 2017 and 2018. And I only lasted at Google for a year. It was actually a ton of fun. It was a lot of fun. But unfortunately, I developed what my PhD advisor later told me was a pathological condition called math envy. At Google Brain, I was sitting alongside so many researchers that I decided I wanted to be a researcher too. So I left Google to start a PhD at Stanford. I worked with this guy here, Stephen Boyd. Some of you guys may know him as the father of convex optimization. He's wrote this very seminal book. Um, and um, while I did eventually satisfy and cure my math envy while working with Stephen, I also did work on software uh, for researchers who worked on optimization. So I was one of the core developers of CVXPy during my PhD. And the ethos of CVXPy is to make it really easy for researchers and developers to use modern optimization solvers. Um, Basically, it lets the researcher specify their optimization problem in a really high-level mathematical way, extracting away all the gnarly, incomprehensible sort of data structures that solvers require in order to solve problems. Um, and now CVXPy is used across the world at many companies and many universities, downloaded millions of times a month. And this was the second time in my career where I experienced how building better tools for researchers can in turn yield better research and more research and can be some of the highest leverage work that you can do. So then that leads us to this talk. At the end of my PhD, last year or two of my PhD, I focused exclusively on um, developing a framework uh, for embedding, for finite dimensional vector embedding. So this talk is about me satisfying my math envy, in other words. So minimum distortion embedding is an embedding framework that generalizes centuries-old methods like PCA, as well as more modern methods like the Laplacian Eigenmap and UMAP. And as you'll see in this talk, um, through this framework, um, we can derive basically dozens of what were previously thought of as different embedding methods or dimensionality reduction methods. We can derive them all as instances of the same optimization problem, and we can solve them by using just one optimization algorithm. And this algorithm, as you will see, it's called a Quasi-Newton algorithm for non-convex constraint optimization. And we can use this algorithm to solve uh, compute these embeddings efficiently at scale and in a very GPU-friendly way. As I mentioned right before the talk began, this paper or book it is really quite long, but it is available free and online. And the reason it's long is that we really take the time to explain all the concepts in really great detail. So it actually hopefully shouldn't be too difficult of a read. And afterwards, if you're interested, you can check it out. Just Google minimum distortion embedding and you will find it on AlphaKive. So um, at this point in my career, when I was working on this monograph, I now well understood the value of building software tooling for research rather than just doing the research alone. So there is an accompanying open source package called PyMDE. Um, that lets you compute these embeddings, uh, perform dimensionality reduction on GPUs. It's implemented with PyTorch under the hood, um, and it's free and open source, and you can find it online. Now, before diving into the embedding framework, I'd like to talk about just one more thing, and it's about what I work on today. And then after that, I promise we're going to get into minimum distortion embedding, the math, all of it. So I finished working on minimum distortion embedding at the end of my PhD, and by this point I was 100% cured of my math envy. I was satisfied that I could do math, I could do research, that was all great. But really all that I was left with was a desire to make software tools that made researchers more productive. And instead of thinking about specific research tasks like deep learning or convex optimization or dimensionality reduction, I zoomed out and started to wonder what was the highest leverage thing that I could build to help researchers at large in general at scale. And what I landed on was actually Python notebooks, believe it or not. So it's no secret that a ton of research starts in Jupyter notebooks in particular. And famously, Alec Radford, one of the original creators of GPT and CLIP, supposedly codes exclusively in Jupyter notebooks. And I personally made all the plots for my thesis in Jupyter notebooks. And the reason that researchers, I think, like notebooks is because it lets them iterate on algorithms and ideas in memory. You get immediate feedback with plots and other outputs as you execute code. And so, as you can imagine, like notebooks are really useful when I was working on dimensionality reduction algorithms because I could sort of see visually what my embeddings of high dimensional data down into low dimensional data vector spaces, I could see what they look like. Um, so it's no secret that a ton of research starts in Jupyter notebooks, but it's also no secret that a lot of people don't like Jupyter notebooks. And in fact, many researchers, even though they use them really widely, don't like them and sort of have like this love-hate relationship with Jupyter notebooks. At least I did when I worked on my PhD and also at Google Brain when I worked on demos. And so I can at least speak for my reasons that I think traditional notebooks fall short. So one is like limited interactivity. So in this plot here, what you're looking at is a 2D representation of the MNIST data set, where each point represents an original digit from 0 through 9. And they're clustered together, so similar digits are close together. But surely I had outliers in there somewhere. And in a Jupyter notebook, my charts were static, and I wasn't able to trace the embedded points back to the original high dimensional data, and that was really frustrating. And then other reasons I struggled with Jupyter notebooks was like this kind of hidden state led to like really weird um, inconsistencies in state where like the first cell says x equals 1, but then later you see x equals 0. And then because Jupyter notebooks are not stored as code, you get these really, at least, man, my directories looked like this after, not a lot of time where I would just be littered with untitled PyMDE files in my folders. And then because of that, like versioning with Git was a total nightmare. And then ultimately, like, my research and other colleagues who I worked with, like when we did our work in Jupyter notebooks, like the work just didn't reproduce. And that was really frustrating. And so that convinced me that the highest leverage thing that I could do for researchers after finishing my PhD was creating a new type of notebook. And that notebook is called Marimo. It's stored as pure Python. It's reproducible. It's highly interactive. This is a little GIF of a Marimo notebook that we'll see live in just a moment. And because it's stored as Python, you can import functions from your notebook. You can execute it as a script. Marimo was open sourced a little over 2 years ago and now has tons of GitHub stars, tons of usage, is worked on by a really rock star team. Some of them are in the audience here today. For better or worse, we have 3 PhDs on our team. Depending on who you ask, that's a good thing or a bad thing. Um, but I think it's a good thing. And I just want to call out that we are hiring. You can go to marimo.io/careers if working on tools for researchers excites you. And with that, let's talk about embeddings. So minimum distortion embedding. This is a version of a talk that I gave in 2021 at the end of my PhD at Stanford. So the contributions of this research monograph, which was published in Foundations and Trends in Machine Learning, is really just two high-level ones. The embedding framework that unifies a century's worth of work on embeddings, and two, a novel algorithm for approximately solving these embedding problems, and just one algorithm. So let's start by talking about what an embedding is. In this context, an embedding is a representation of abstract items labeled 1 through n by vectors x1 through xn. And these vectors are in some, dimension vector space in Rm. We use m to denote the size of the embedding vectors. You can use these embeddings if m is 2 or 3. You can use embeddings for data visualization or insight. If it's higher, you can also use it for downstream computational tasks. The point of the embedding is that it should be faithful to the original data in some way. And in particular, this is the loose sort of English definition that is actually very close to the mathematical definition that I will show shortly. So if two items are similar, their vectors should be near each other. If two items are dissimilar, the vectors should not be near each other. They don't necessarily have to be far, but they just shouldn't be near each other. And similarity is a property of pairs of items, the items 1 through n, and is application dependent. So if the items are images or biological cells or whatever, but that depends on the application. But nearness is a property of pairs of vectors, and that is a mathematical property that we measure in Euclidean distance. So let's look at one example that I sort of alluded to earlier. This is the MNIST dataset. It is a classical dataset used for a lot of classical machine learning tasks. It's a collection of 70,000 images of handwritten digits, 0 through 9. And I'm going to show you an embedding that I made using the embedding framework by taking 1.5 million pairs of similar and dissimilar images. And then we embed into m equals 2 dimensions, meaning we can plot it. So this is the embedding. It's a scatter plot where each point here is a different is an embedding vector. So in R2, and each point represents an original item or digit, handwritten digit, and the scattered points are colored by the digit class that they belonged in. So you can see in the embedding, most of the zeros are clustered near each other, all the ones are near each other, and so on up till 9. So you can see this embedding is faithful to the original data set. And like I mentioned, I didn't just work on the math for this, I also worked on software. And so you can compute this embedding with PyMDE, and to sort of close a loop, you can also visualize it in a Marimo notebook. So here you're looking at an example of a Marimo notebook. We can share links to these notebooks so that you can run them too after the fact. It shows how to visualize the MNIST dataset using PyMDE. The details and syntax are not too important, but there's this one function here called PyMDE.preserve neighbors. You pass it in your dataset, and then you pass it in the embedding dimension and some other details, and you get your embedding out. This is the same embedding that I just showed on the previous slide. But what's cool and what you can do uniquely in a Marimo notebook that is really kind of hard to do in any other kind of traditional notebook is that you can now interactively answer questions about the embedding you just computed using very few lines of Python code. So what I just did here is I made a selection on the chart, and I got the selected points. I got them back in Python. I got the indices of the selected points back in Python, which then lets me index into my original data and get a preview of the images that I just embedded. And with very few lines of code, I can now answer questions that were just like way too hard for me to answer in my PhD, such as like, in this cluster of points that I've selected, surely not all of them are ones, but most of them are. What do the digits that my algorithm thought were ones look like? So I can do things where like I can sort my selected data by digit and then see all these outliers. Looks like there's a bunch of 9s in here. I can click into here and see and see basically this tells me that my algorithm thought that these digits were ones or close to ones. And some of that kind of makes sense, right? Like, I mean, that's like a pretty wonky looking 9 over there. And the point is that in this notebook, I can answer questions about my data and arrive at insights far faster than I could have in a traditional Jupyter notebook. Back to the talk. So what are some applications of embeddings like this? You can use embeddings for interactive data exploration. You could embed counties or co-authorship networks, genomes, a whole bunch of things. In fact, everything here, PyMDE has been used for all of the above. And more broadly, like 2 main classes of tasks you may use this for: dimensionality reduction for visualization, or compression, or feature generation for supervised machine learning. So a bit about the history. Embeddings of this kind you can trace back at least to like 1901, like PCA and multi-dimensional scaling. PCA actually, both of these methods actually came from early research in psychology, believe it or not. And what these problems have in common are they are all sort of in the mathematical sense tractable. So they reduce to eigenproblems or like linear algebra problems that you can solve analytically and get exact solutions. And so, for example, here on the right is a PCA embedding of the MNIST data set, which, by the way, you can easily compute in PyMDE. In Marimo, you can have UI elements as well. So I've already pre-computed these, and I can toggle from my algorithm to PCA, and then you can see the PCA embedding down here. Um, then from the 1990s to the 2000s, so whereas previously we had PCA, multidimensional scaling, the focus shifted to dimensionality reduction methods. These were called in the literature manifold learning because the idea was like you were trying to approximate some manifold. And there were like tons and tons of these methods like isomap, locally linear embedding, Laplacian embedding, maximum variance unfolding. You may have heard of some of these. It turned out that like all of these actually were also entirely tractable and also reduced to eigenproblems that you could solve with an analytical solution. Um, Again, you can also compute these in PyMDE. I have sort of pre-computed one here. I can switch to Laplacian, and you see that same embedding out. And you can do the same sort of data exploration trick we were doing earlier. And now 2000s to the present, what changed was in these embedding methods was a new emphasis on solving in quotes, because you can't exactly solve these problems, but solving non-convex problems. And so these are methods like TSNE or TSNE, large viz, UMAP, and of course a neural network. In the mathematical sense, these are not tractable. We can't guarantee we get a solution to them. But in practice, we can develop heuristics that work really, really well. So this talk is about a general framework for faithful embedding. It exactly reproduces many historical examples. In fact, all the ones I just showed you on the previous slides. It approximately reduces others, and it also generates new kinds of embeddings. And then also an efficient heuristic optimization algorithm. I will say that this embedding framework does not include neural network based embeddings. Those are sort of, a different methodology. Here we focus on where you have like a finite universe of items that you want to embed ahead of time and don't necessarily generalize to unseen data. However, there are ways that this methodology could be extended to handle that. Any questions before we get into some of the math?
Actually, there are a few questions, Akshay. The first one from Jacko. Actually, if you're in here, I could just invite you to unmute. Uh, okay, I can just ask the question. So they're asking, is there a way to guide the clustering of embeddings? Like, let's say I have some labels and I want to influence how the clusters are formed.
Yeah, 100%. And actually, that's what a lot of this talk will be about. It's about choosing the parametric form of your objective function. So we'll see some examples.
Sweet. And then there's another question, which I think somebody else answered, but is this kind of generalizable to any type of data?
Yeah, yeah. In fact, it's like pretty agnostic to the data. All you need for the original data is some some notion of whether pairs of items are similar to each other. And you can either compute that algorithmically if like the original data are vectors. If they're not, like you can also have whatever, some kind of oracle or some kind of procedure to assign similarity or dissimilarity. But you can think about it as like a pre-processing step for your original data.
Cool. Um, Nikhil is asking, is this technique, can it be, or I guess you answered, you can't represent the neural network state with,
No, no, this
yeah,
is pretty different. A little bit more focused on dimensionality reduction of high dimensional vectors.
right. And does this work for both categorical and continuous variables?
Yeah, yeah, that's totally fine. I think that goes back to like the original items are abstract, and it's sort of the embedding author's responsibility to come up with um, a notion of similarity on that sort of abstract space.
Cool. I guess the last fun question, and then I'll let you continue. But somebody asked, "What are you using to present this? Is it not a Marimo notebook?"
Okay, so this is okay. The first one was actually not a Marimo notebook. This is TL Draw, because I was a little too lazy to create new slides, and this was kind of fun. This is my LaTeX PDF. I do have, okay, here's one. I'm actually not going to go through this, but this is a Marimo notebook. Um, it's like slides. It's like kind of awesome. Miles implemented this slides feature. Miles, I think he's in the call, implemented a lot of Marimo's functionality, including this. Um, yeah,
Awesome.
it's kind of awesome, right? But
Yeah,
no, I'm actually not working through the Marimo example right now. If I have time, I could come to this, but we're going to be using old school LaTeX slides right now.
awesome. Yeah, there's a ton of interest in the chat I'm seeing for learning more about the tools. So yeah, you guys should totally have to once your talk is done, like send over some more resources, and happy to pass those along as well.
Cool, we'll do. Um, Yeah, and I guess like if for these notebooks, I can actually just show you quickly. Like if you want to follow along with any of these, most of them should be, or all of them should be online now. So if you go to pymde.org/examples, it's like this MNIST notebook we just looked at. You can click this button here, open in MoLab. MoLab is like Google Colab for Marimo, and we just like ripped off the name. But you can click it, and then it should take you to this page. You can click Run in MoLab here, and then you can start running this and sort of following along and playing with the embedding as well.
Awesome. Yeah, and I mentioned earlier for everyone here, but AlphaChive and Marimo are really working together, and they're providing us with implementations through the notebook. So here's just an example on a GDPO paper. Check out the resources tab. There's a link to their notebook. So
Yeah,
yeah,
and I guess if anyone uh, else wants to help or be involved, like I think it would be a lot of fun to like sort of crowdsource like research re-implementations and like Marimo notebooks or MoLab notebooks. Right now we don't have free GPUs on MoLab, but they are coming. And if you really want GPUs before they're sort of GA, you can reach out to us, and we can see what we can do. Okay.
awesome.
Any other questions, or should I get back to it?
Brian just asked, when is the CoreWeave sponsorship? So,
What is the core? Yeah, so Marimo is part of CoreWeave, but there's no mention of CoreWeave in this talk. Um, We could talk about that some other time, but it's actually been really, really awesome being part of CoreWeave. And it's actually enabled us to really double down on the open source and on MoLab.
awesome. Cool. Yeah, I'll let you continue on.
All right. Okay. So a bit about the math, hopefully not too much, or if you like math, we can go more into it. So an embedding of items, script V, so 1 through n, embedding of these items is a matrix X in Rn by M. So the number of rows is the number of items you are embedding, and the number of columns is the embedding dimension. Um, and you can think of the M columns as features, and the rows themselves are the embedding vectors. So like x1 transpose, the first row of X, is the embedding vector for the first item. And in the examples we've been looking at, you can think of 1 through n as the MNIST digits, and then X as the thing that I showed in the scatter plot. So distortion, the framework is called minimum distortion embedding, and we want the embedding to minimize the distortion of the original data. So the quality of an embedding is a function of the distances dij, which is the Euclidean distance between xi and xj. So the ith embedding vector and the jth embedding vector, where ij are part of some set script e, which is a subset of v cross v. So basically, it's just like a set of edges. And each pair ij has an associated distortion function, fij, which maps the embedded distance to some scalar value. And the Fij are things that you, the embedding author, choose, and PyMDE basically has like sensible defaults for them in some high-level functions. But to the earlier question of like, oh, can you influence what the clusters look like? You can. It's through these Fij. So the distortion of the embedding for a pair ij, so for example, a pair of digits that are either similar or dissimilar, is Fij applied to Dij, so Fij of Dij. And so some basic examples of what you could use for your function Fij, you could say Fij applied to Dij is Wij times Dij squared. So here, Wij is a weight or similarity score. So if it's positive, that means things are similar. Negative, they're dissimilar. Or you could have Fij of Dij be um, the difference between the embedded distance and some original distance squared. And so here, delta ij is a deviation or original distance. And so this gets us to the optimization problem that I have been alluding to. And the optimization problem is this. Um, the variable optimization variable is x, the embedding matrix. And the goal is to minimize e of x subject to x belonging to some constraint set that we represent with script x. So here, x in Rn by m is the variable. E of x, which you can kind of think of as like the energy of the embedding if you want to think of a physics interpretation, is the average distortion. It is the sum of all the edges in your edge set of Fij applied to Dij. So it's the sum of the distortions that of your embedding, and then normalized by 1 over the size of your edge set. And like I mentioned, the script x is the set of allowable embeddings. So I guess some things to note here. The main thing to note here is that the objective function only depends on x through the embedding distances, so these Euclidean distances. And then also the objective function is separable over the Fijs, meaning it's separable over pairs. So if you like, these two things are interesting because you can exploit them to implement really efficient algorithms. Like if you want to parallelize the evaluation of the average distortion, which we do in our software package.
Just to make sure everyone's on the same page, Akshay, does distortion roughly, in terms of intuition, kind of measure how well the embedding, how like how well it captures the desired relationships between items, like how
Yes,
similar
yes.
how similar the embeddings are to what they should be? Is that
Yes,
kind of a
that's
good way?
exactly it. Yeah, yeah, that's a good question. That's exactly it. So originally we talked about there's this notion of similarity in the abstract space and like nearness in the original space. So Fij is that thing that's it's the distortion is the bridge between like, hey, like, an image of a one and like, I don't know, an eight, those things are not similar at all. So Fij, so like the distortion for that, if the distance between a one and a eight is zero in your embedding, if they're right next to each other, that should have high distortion. Um, Whereas if they're not close to each other, that should have low distortion. Great question. So yeah, in English, the goal is to minimize the distortion to whatever known relationships you know for your original data, subject to some constraints on your embedding, and we're going to see some examples of constraints in a moment. So solving MDE problems, like, okay, if you, in the mathematical sense, that it's like intractable, except in a few special cases we'll see later. Intractable meaning like you cannot guarantee that you can find the global minimum of this problem, but we're going to develop an algorithm that approximately solves these, and it reliably solves tractable problems, and then reliably finds good embeddings for others. So some examples of distortion functions, just to get a little bit more concrete is there's basically two classes that we implement in the software package. So one parametric form is distortion functions from weights. So each pair of items have a weight associated with them. If the weight is positive, that means the pair of items are similar. If the weight is negative, they're dissimilar. And the magnitude of the weight conveys the degree of similarity or dissimilarity. In the simplest example of a distortion function that sort of is measuring faithfulness that uses weights, just multiplies the squared distance by the weight. Um, Here's a sort of more complex example, um, but it's a very useful one. So if for a weight that's positive, then take the distortion function to be the weight times log of 1 plus the distance squared. If the weight is negative, meaning the items are not similar, then take the distortion function to be the weight times 1 minus e to the negative distance. It's more easy if you just like look at the plot. And so basically what this says is you have zero dis for the blue curve, that's the top equation. For the blue curve, that means that two items are similar, then the distortion is zero if the items are placed next to each other, if the embedded distance, which is on the x-axis, is zero. And then this is what I was saying of like if two items are dissimilar, well, if the distance is small, you get high distortion, but if the distance as the distance gets larger, the marginal utility you derive from making them farther and farther apart goes to zero. So you just don't want to put them next to each other. You don't want to put the original items next to each other, but you're okay if they're not super far. And so that's, I guess, what it says down here in the bottom. This captures the basic idea of faithfulness that vectors for similar items should not be near each other, and vectors for dissimilar items, um, similar items should be near each other, and dissimilar items should not be near each other. And if anyone in the audience has used like UMAP, basically you can recreate UMAP by like using these kinds of these two distortion functions and setting wij to be +1 for similar items and -1 for dissimilar items. And it turns out you don't need any of the sort of more complicated machinery that's sort of in that paper and sort of related papers, at least in my experience. And then the other example of distortion functions that we use sort of in the software package are from deviations. So here, like you have an original distance in the high dimensional vector space or whatever the abstract space that you're trying to preserve, delta ij, and the distortion function is minimized if your embedded distance matches your original distance. So if dij matches delta ij. And so some examples here that you could use, again, mathematically, classically, the simplest thing is the quadratic dij minus delta ij squared. And I think that recovers multidimensional scaling, this method from like the 1930s. There's tons of papers about multiple dimensional scaling, but it's just that. It's a quadratic deviation. Or you could use an absolute function, you could use a fractional function, and these just depending on what you want out of your embedding, how close or how far, um, what kinds of distortions you're willing to tolerate. Um, that might affect your choice of distortion function. And one thing that's really nice about using an environment like Marimo is that you can kind of just shape these functions and like kind of just really quickly see um, like how the choice of uh, function impacts your embedding. Um, I don't have the best example here, but like um, you could imagine like creating like a slider or something that impacted the weights. So in Remo, you can do things like you can create a slider with mo.ui.slider 110, output it here, and then output the value in another cell. And then you could like notice how I'm changing the slider value here. The value of the UI element is changing as well. So you can use primitives like this. You can imagine using them like this to set up like an experimentation pipeline to like see how different choices of parameters affect the embedding that comes out. By the way, I guess we probably won't have time to really go into the details of how Marimo works, which is why I won't go into my Marimo slide deck. But the TLDR is the way that it works is that the reason that like these UI interactions are flowing into the Python code is that um, Marimo actually statically parses your notebook as a data flow graph and knows how different cells are related to each other. So for each cell, it knows what are the variables it defines, what are the variables it references, and what are the other cells. Yeah, what are the variables it defines and what are the variables it references. From that, we form a graph so that when we run one cell, or if you run a cell, or if you interact with the element, Marimo knows what other cells need to run in order to keep code and outputs in sync. So this basic primitive is what enables a Marimo notebook to react to your code changes. It enables Marimo notebooks to double as like web apps. to double as slides, as I showed earlier. It also enables Marimo notebooks to double as well-formed Python scripts a with a well-defined execution order that can be run as scripts. This is the file representing the embedding notebook you're looking at. It's also what enables the static analysis is what enables us to do things like from my notebook, import my function. So you can see like this one function here is uh, defined top level. Um, you could, and I have, give a whole talk just about Marimo and all the ways that it sort of uh, really levels up your research workflow. But hopefully, this is sort of a hint of how Marimo may do that. And if you are interested, you can go to docs.marimo.io to learn more, and you can install it locally with pip install Marimo. Oops. Okay, back to the talk. Um, so we just covered two classes of distortion functions from weights and from deviations. Um, but then, okay, the natural question is like, okay, how do you come up with these weights and how do you come up with these deviations? And so in using this framework, there is like a pre-processing step. So it's often useful to pre-process the original data, the raw similarity data, in order to come up with your weights or your deviations. And the honest truth is like this is sort of like an art. It's kind of like classical feature engineering. Um, but there are some recipes that work well that we've implemented in the software package. So let's assume for a moment that we have some like original notion of distance in the original space. So like for the MNIST example, for example, like you could even like because images are can be represented as vectors, right? You could even just say like the Euclidean distance between two images is like the original deviation. And so one way to get weights in a way to influence clustering if you want to emphasize the local structure of your embedding is to do the following. Um, Calculate the k nearest neighbors of each item, k is a hyperparameter, to get similar pairs. So for each item, find its k nearest neighbors, and each of those is considered similar to it. And then use wij equals +1 for neighbors, and then optionally use wij equals -1 for non-neighbors. And then to emphasize global structure, compute the shortest path distance on your original data. So you have pairwise original data. Now compute the shortest path between your original data, between items in your original data, and then set up distortion functions that preserve these shortest path distances. And so both of these are implemented in PyMDE. If you do PyMDE.preserve neighbors, it's going to emphasize local structure. If you do PyMDE.preserve distances, it will emphasize global structure based on the shortest path metric. Um, so we haven't talked about constraints yet, but I mentioned that you can constrain your embedding in PyMDE and in the minimum distortion embedding framework. So one natural constraint is the centering constraint. All it does is like centers the embedding vectors around the origin. And like this is without loss of generality because the distances are not affected by translation. And it's just a way to just have like sane, um, like a sane sort of representation of your embedding, say on a plot. Like it doesn't really make sense for them to just be moving around in the vector space. You can kind of think of centering as unconstrained. Another interesting one is an anchoring constraint. You can pin embedding vectors for anchored items in some script K. And so this is useful for like incremental embedding. If you are like you know where some items should be, or you've already computed an embedding, so you pin the existing embedding and you want to add new points to your embedding. It's also useful for like graph layout problems. And one thing we really won't probably have much time to go into here, but like some of you guys may have heard of packages like Network X, which are used for graph layout. Um, that is also like basically most, if not all, graph layout algorithms are special cases of the minimum distortion embedding framework because you just use you use distortion functions derived from original distances. And it's not just like a theoretical thing. Like you can use PyMDE to like lay out graphs in ways that are like far faster and like more flexible than like Network X. So this is an example of a graph that I laid out just for fun. Um, I um, and I pinned some of the items to be on to be in a circle, and then you just kind of get these like kind of basic. This is basically just art, but it's kind of fun, and you can use it sort of for more practical applications if you just want to algorithmically lay out graphs in sort of aesthetically pleasing ways. Okay, and this is just for fun, but in PyMDE, like the GIFs that I had in the beginning of the talk, you can create a GIF for any embedding that you make, and then you can just share it on social media, and then get a bunch of likes and stuff. At least that's what I've done historically. Um, okay, back here. And the third constraint, this is the most interesting constraint, it's the standardization constraint. It says 1 over n, so n is the number of items, but it says 1 over n times x transpose x is equal to the identity matrix. And then it's also centered, so x transpose 1 equals 0. So in English, this means that the feature columns are uncorrelated with root mean square value 1. It also forces the vectors to spread out, but not too much. So this actually prevents the embedding from collapsing to 0. So it's a very useful constraint to have in many cases. It's also a totally non-convex constraint set, which makes the problem sort of more difficult to solve. Okay, I'm going to start speeding through and maybe I'll end 5 minutes early for questions. Um, so some historical examples come from this what we call a quadratic MDE example. So take the distortion functions to be a similarity score times dij squared, and then use the standardization constraint I just introduced. If you do this, you can solve this problem exactly using eigenvectors of a certain matrix. And then it turns out PCA, Laplacian Eigenmap, kernel PCA, isomap, locally linear embedding, classical MDS, maximum variance unfolding, and like other algorithms, they are all just this. There's nothing more special to them than just like this form. They only differ in the way that they choose what Wij is and what the edge set is. But otherwise, they're exactly the same algorithm. So some examples for PCA. Um, Actually, I think this one is actually really pretty interesting, gives you an intuitive understanding of what PCA does. So PCA starts with a data matrix in Rn by P with rows Yn through Yn. So that's the original data. And the embedding, the solution is to take the top m eigenvectors of YY transpose. It turns out if you do some math, you can figure out that this is equivalent to solving a quadratic MDE problem with Wij equal to the inner product between Yi and Yj, and you take all the edges. So you form all the edges. And the interpretation, I think, is actually really kind of nice. What this says is that items I and j are similar if the angle between them is acute, and they're dissimilar if the angle between them, if the angle between the original vectors is obtuse. That makes sense. And it also says that the embedding is neutral to items I and j, to the relationship between them, to the placement of items I and j, if yi and yj are orthogonal. And that makes a lot of intuitive sense, but it's, I think, rather beautiful to see it sort of laid out in this way. The Laplacian Eigenmap is another really famous example. Turns out this also can be reproduced exactly using MDE. I'm going to speed through this. UMAP. Oh, okay. I guess I misspoke. It's been a little bit. These are the distortion functions for UMAP. They're very similar to the ones that I showed earlier, the logarithmic ones. Um, and what I found is like actually all these hyperparameters don't matter at all. The alpha, beta, gamma, just like set them to 1 and it just kind of works well. Okay. In 2 minutes, we can talk about the Quasi-Newton algorithm we developed, and then we can take questions, or I can go longer, whatever folks like. So here's the algorithm. I think it's kind of awesome. Stephen Boyd helped me a ton as we developed it. So some prerequisites. The tangent cone to the constraint set is defined to be the set of vectors in Rn by m, such that like the distance if you move in the tangent direction is like little o of h. So if you take like a tiny step, you basically don't leave the constraint set. So it's like similar to the notion of like tangent to a curve. And so a vector is called a tangent to the constraint set if it belongs in the tangent code. And then a direction is a feasible descent direction. So we're talking about descent algorithms, kind of like gradient descent, right? So V is like a direction you step in at any point in the algorithm is feasible if it's in the tangent cone, and if the inner product between the gradient and the tangent is less than zero, meaning you descend. That's what that means, the gradient of the objective function. And so an embedding is stationary, not necessarily globally optimal because you could have like multiple stationary points, but it's stationary if the cone of feasible descent directions is empty. All right, I'll go 2 more minutes and then I'll stop. A stationarity condition is when the if you take the gradient and you project it onto the constraint set, the stationarity condition is the projected gradient equals zero. And this is equivalent to saying to solving this optimization problem. The paper explains this in far more detail. Um, the algorithm that we develop requires projecting onto the constraint set and onto the tangent cone. And it turns out you can compute these projections analytically, cheaply, really efficiently for the centering constraint, for the anchored constraint, and for the standardization constraint. The last one is sort of the most complex one, but it's really not that complex. Requires computing the SVD, which in our case, because M is usually really small, you can do really efficiently. And a traditional gradient method is the projected gradient method, which some of you may have heard of. It's just you compute the gradient, you choose a step length, and then you move in the direction of the gradient and you project down onto the constraint set. So that works. It looks like this. You might be at xk, you move in the direction of the negative gradient to descend, and you come back onto the constraint set. So that's this curve here, xk plus 1. It works, but it's like crazy slow. So something that is slightly faster, but is still really slow, is to project twice. Is instead of moving the direction of the negative gradient, you take the negative gradient, project it onto the tangent set, uh, and then move in that direction, and then move back onto the constraint set. So the gradient's projected, and then the next iterator is also projected. So that works, still slow. And what we developed in this algorithm is an extension of LBFGS to handle constraints. We call it a projected LBFGS method. It appears to be new, but it just combines some old ideas. It's related to some manifold optimization stuff too. It works and it's extremely fast. And the basic idea is if you're familiar with LBFGS, you just like replace the gradients with the projected gradients, and then you project back onto the constraint set. And I'm gonna skip the math, but it's really fast. So like this is like uh, the convergence, the time to convergence for an optimization problem for the embedding method. And the point is the black one is the projected LBFGS one. The green ones are like projected gradients. And this shows what is, if you're familiar with optimization, sort of called quadratic convergence or close to it, where just in a few iterations, you just basically nail the whole problem. Um, Software is available online, PyMDE.org. It's implemented with PyTorch under the hood, so it's super fast. I wanted to show you guys this embedding of Google Scholars, of authors from Google Scholar, but I don't really have too much time to explain it. But this is a co-authorship network where the original data was like whether two authors had written papers together. And then I just plotted them, preserving the original graph distance. And you can kind of just explore where professors end up, where different fields end up. It's pretty fun. Um, you can look for your PhD advisor or your ideal PhD advisor. I can try to find mine. And there he is somewhere in the middle, which makes sense because I scraped this data by starting with him at the middle. Um, this example is also online at pymde.org/examples, so you can play with it in MoLab. Um, I have a minute left, so I'm going to stop. But thank you guys for listening. Hopefully it was enjoyable.
Thank you so much, Akshay. That was so awesome, and yeah, there's a ton of questions and interest in the chat.
I
So
can stay over if folks have time, but I'm
That
Uh,
would be awesome. I
okay.
think somebody in the chat was like, I'm down to stay an hour. Obviously, you don't need to stay that long.
Sure.
But I guess one quick question I had, and then I'll like hand it over to the audience, but like kind of forward looking in terms of like, what do you think has changed in the field since like 2021? And what would you explore now with like all this hindsight of like the context of like LLM era embeddings?
Yeah, it's a great question. So I mean, so I think that these kinds of dimensionality reduction are still useful for like exploring like a space in like a snapshot of time. So like if you have some if you have a data set and you're looking for outliers and trying to cluster, I think they are really quite useful. I think they're less useful for feature engineering. Like I think with LLMs and I mean it doesn't have to be LLMs, just neural networks. Like the whole point is um like they're like representation learners or feature learners, and it turns out that they're like semi-supervised or unsupervised learning. Semi-supervised learning, you can get really good embedding representations, and so I would probably go that way for like, especially because that generalizes to unseen data. Um, there's probably some really interesting research work to do to like, I don't know, better understand like the class of embedding generating algorithms implemented in neural networks. That's something that I haven't really had the time to look at, but something that I would love to look at if I if I did have more time. Yeah.
Awesome. Also, for folks who have to head out, we will be posting a recording on our YouTube channel, which I dropped in the chat. Also, Akshay, if you have a good email to reach out to you or anything, that would probably be really
Yeah,
helpful.
yeah. You can should I drop it in the chat or
Yeah, that would be awesome. While that's while you're doing that, um, somebody asked, are there any failure modes of embeddings that become apparent only through the interactivity that Marimo allows?
Yes, there are. Actually, I had an example. This is a great question. So I did this example. Uh, where I took a bunch of US counties. This is in my thesis. I took a bunch of US counties and then like embedded them. And then I was like, oh my God, it kind of looks like the United States. Like what comes out. And actually, this is a funny anecdote because like there's this guy who I think like won the Nobel Prize for doing something similar for like genomes of like PCA and like it kind of looked like a map of Europe. But like honestly, like most of the time, like things like this, it's kind of like reading tea leaves and it's kind of BS. So like here, these are a bunch of US counties, and you're like, oh, okay, like maybe this is like Florida or Texas or something, but like it's totally not. Like it's just like a total coincidence that like this looks like the US, even though like you can see, oh, I don't know why it keeps on rerunning, but like there's like California, Colorado down here in the south uh of the embedding. So that's one way, and I think the other, I'm not sure if it's exactly a failure mode. I guess it could be is like what I was showing earlier with MNIST of like get a cluster, sort, look for outliers. Maybe not exactly a failure mode of the embedding, but it can be a failure of like you can find weird things in your data set that maybe shouldn't be there. Like if you're embedding things should be close together, but their distortion is high. I think that's the thing. Like you can create the embedding, then look at the CDF of distortions and find points that have high distortion, and then just like kind of dig down into that. So that's another thing I might do.
Awesome. Abhijit, are you here?
Yeah, sure. I can go next. So, like, I think there were a couple of questions around, like, what kind of, like, what family of distortion functions we can choose from, and like, also, are there any limitations, like, while choosing the distortion function,
Yeah.
and
Oh,
also
sorry.
whether the distance, does it have to always be a metric, or it works with like non-metric distances as well?
So for the distortion functions you choose in practice, like I mean you can do anything. It should hopefully be efficiently computable by PyTorch. It doesn't even have to be differentiable, ReLUs are not differentiable. You can use absolute value things and it kind of works. Um, flexibility in the metric, like f- in the optimization problem, everything is in the embedding space. We use Euclidean distances, and that works well in practice. In the original data, it doesn't have to be a metric if you like the original deviations, but things might be kind of weird if it's not. Um, but I haven't thought about that too much.
Awesome. There's a really interesting question I guess kind of related to something you were talking about earlier, but like they're asking the dominant embedding paradigm in recent years has shifted towards learned representations from foundation models. Do you see MDE as complementary to these, say, as a post hoc refinement layer, or has this problem been subsumed by representation learning? Is there a principled
Yeah, yeah,
way?
that's a great question. Oh, sorry, did I
Oh,
cut it
sorry.
off?
Oh, I mean, it's just follow on. Is there a principled way to compose MDE with neural embeddings?
Yeah, so I haven't at the end of my PhD I was thinking about that last thing, but then didn't really spend much time. So there probably is, but I haven't really thought about it. Oh yeah, I mean, so some weird things we did in my PhD. So we made like CVX pi differentiable. So like you could drop a CVX pi problem and like differentiate through the solution map. You can do the same thing here. I just haven't done the work. So you could put an MDE problem in a PyTorch layer if you wanted to. I had to think about what that gets you. It hasn't been, this framework hasn't been subsumed um, by traditional methods, by modern methods like by neural networks. It's more that like at least I personally use this kind of stuff when I just want to get a better handle at what is the data I'm looking at. I might not use these necessarily for like feature engineering or feature representation, although you still could, especially if you're working on like I know it's trendy in like, ML AI to think about like, super large scale AI problems, but like also like you may just at some point in your work be making some classifier that deals with the US counties or zip codes or something. In cases like that, like you can just like just embed the entire universe of zip codes and use those as features in sort of your original data in your machine learning pipeline. Um, there's a funny anecdote where I think something like MDE could still be useful, TSNE or PCA or UMAP or whatever, is like I think like when OpenAI was training one of the original GPT models, I don't know which one, like there was a point where like, they're watching the loss curve, everything's fine. But then all of a sudden like the loss just like spikes and people are like, what the hell happened? And I think like I don't know if it's totally apocryphal or not, but apparently it took like quite a while to figure out like what was the data that like contributed to this like crazy spike. And it turned out it was because there was like some mini batch that was just like a bunch of posts from r/microwave gang where apparently our microwave gang they just like respond to posts with MMMMMMMM. So it's just like totally messed up like the next token prediction. But like when you're doing like debugging work like that, it's like often useful to just get a batch of data, make a plot of it, look at it, just quickly try to find outliers and then like move on. So it's like a tool in your sort of data analysis toolkit.
Akshay, if it's okay with you, can I add one thing to what you just said that I think is useful?
Yeah, of course.
So I think Akshay is underselling a little bit the opportunity to sort of compose this kind of workflow with other things. So one very common thing that you want to do is use these really powerful embedding models as your priors because they bake in such incredibly rich priors, and then take that latent space and use something like this to basically fine tune. And I know I get myself into danger by using the terminology now, but like to basically fine tune your embedding for a specific set of posteriors that you've learned from real user data. This is a really powerful workflow, and I think this kind of stuff is makes that very, very effective where it's kind of a nightmare otherwise. So
I love that. Yeah, yeah, that's a great example.
Uh, Brian, did you have another question, by the way? I think I
I
saw some.
did. I asked a question before the second part of the talk, but you talked about it a little bit. I was just going to ask you if you had thoughts on like sort of non-transitive relations between your input data and how this method deals with that. We had a lot of cases of this where you've got things are close to one another, those things are close to another thing, those two endpoints are not close to one another, and so you kind of have this non-transitive property. Um, yeah.
Interesting. Yeah, I haven't spent many cycles explicitly thinking about it, but I think you can represent it in PyMDE and then just might see what happens. But yeah, I haven't spent much time thinking about it.
No problem. No problem.
Anirudh, are you still here?
Yeah, yeah, I'm here.
Awesome.
So I didn't have an explicit question. I think the work is really interesting, and especially like the interactive demos. I'm having to wallow in a bit of data analysis currently in my internship, so I think Marimo would be really useful. One question that I didn't quite grasp, I think, from the presentation was when you were talking about the prior embedding works. You mentioned obviously PCA, which is tractable, and then you went on to say TSNE isn't tractable and uses some heuristic methods. So that is just something I would like some
Oh,
education on. Yeah.
yeah, yeah. So this is when I'm using the word tractable, it's like in the mathematical optimization sense. Like it's a non TSNE, TSNE, UMAP. They're like non-convex problems. So like technically, like they belong to a class of problems where like they're pathological, such that like I don't know, like roughly speaking. I mean, it's not exactly right, but like roughly speaking, not really in it's like NP hard type of thing, but like in practice, like gradient descent or things like it like can work pretty well. And so that's just kind of what I meant. Like there's no analytical solution, and also there's like no mathematical guarantees that well, at least we know of you're going to find a solution to it. Um, but kind of a I guess so yeah that's what I meant by that. If anyone's interested, like one thing that I found, I think that also this framework is useful for illuminating. Like if you read like I think like the TSNE paper and then like the literature around things like large vis and UMAP and all these things like they spend a lot of time talking about like their optimization algorithm and like you do early stopping or gradient clipping or do this and then that and then you do this and then you do and, like all these weird like heuristics. But I think actually what was happening there is that like they didn't well specify the optimization problem. Plus they had a bad optimization algorithm and then like that's why all these things look like they're unique. But like it turns out if you do the math like we do in this paper, like you can just have one optimization algorithm that's really just general that can solve all of these problems. Um, so I think that's one of the sort of main contributions of this work.
Abhijit actually sent the Reddit subthread that broke the training.
Nice.
Yeah,
Yeah, it's
uh,
crazy.
yeah. Actually, there's another question from Jacko and the Q&A, which is there a way to measure the information lost when reducing the dimensionality, like what you can get with PCA?
There's like so I mean distortion like in this embedding in this framework is like kind of sort of like in a very imprecise way measures that. There's a whole bunch of like pure math you can like get into of like metric embeddings and things like that try to make this really precise. And there's like things like the Johnson-Linden-Strauss lemma and JLT, all these things, um, sketching, all these things. But they're sometimes practical, sometimes not. So
Okay,
I was
that's
originally interested in stuff like that, and then I got over my math envy, and I'm like, I'm just gonna work on practical things. But it is interesting. The math is really beautiful.
Sounds good. Um, yeah, I don't want to take too much of your time, Akshay, so you let me know whenever.
If there's still questions, I can hang on for a few more minutes.
so Akshay, I have a question. So we do still see like a lot of Disney plots in the papers versus the other methods. Do you think that's because like most data sets have the long tail problem, which Disney addresses better than other dimensionality reduction techniques? So what's your take on that?
No, I don't think so. I mean, so TSNE and UMAP and like the kind of MNIST things that I showed, what they do is they emphasize like the local structure, which is useful, whereas PCA is maybe you can reason about better, but like it's just more global and it's everything gets smeared together. Um, TSNE like kind of works. You see a lot in like biology and stuff too, where like they probably don't care too like if this already works, like why would I kind of change it? Also, like there's like a cultural thing. If everyone else is sharing T-SNE plots, regardless of whether you know how to interpret it, you're like, okay, I should share one too, so like other people can also interpret it. Um, I also, as soon as I finished PyMDE, I like kind of pivoted hard into working on Marimo and didn't spend much time marketing it. So there's also that. Um,
Cool. Mark, are you still here?
Yes. So you mentioned manifold optimization, which the tangent made me think of. You went through the math too fast for me to follow, but is there something like a second order attraction versus first order attraction thing going on with your algorithm? Is that kind of the essence of it?
Yeah, yeah. So yeah, the algorithm's explained in much more detail in the book slash paper. Um, So I will be the first to admit I did not do a big deep dive into manifold optimization. It looked like vaguely related, and I think it is, but the machinery was pretty complex, and I just didn't. But yes, it is basically it's like I think the way that Steven described it is that we're we're in LBFGS, you are building up um, like a representation, like a first order approximation of the function. Like yes, in this case, like you're building up an approximation of like the curvature of the function by doing the projections onto the tangent cone. Um, that was like I think loosely the idea behind it. We didn't do the theory, so we did this. We're like, wow, this works really well, and then we didn't do any of the theory to prove that, oh, this works in this case or that case or what exactly it's doing. And I was kind of hoping someone else would do it so I could learn about
So,
it, but it hasn't been
so I
done.
think in manifold optimization, you get the Riemannian gradient and maybe Riemannian Hessian if you're doing a second order method, and you
Yeah.
take some step there. And when you take that step, you now go off the manifold. So to keep the algorithm going, you have to do a retraction to get back onto the
Yeah.
manifold.
Yeah,
And that's
yeah.
where I think you kind of blow the ball game on a lot of the manifold optimization. I think almost everyone does first order retraction, which kind of seems to throw away most of the advantage of the Riemannian optimization. You do a second order retraction, you give up it may take extra computation, but you give up a lot less of what you just gained by doing that Riemannian optimization in the first place. So maybe
Yeah.
by you're doing the LBFGS, you're sort of getting that second order traction kind of thing going on through
Yeah, I think
the
that's probably
Lagrangian that's sort of doing that, like a
yeah, I
second
think that's
order
probably
attraction
it.
method.
I think that's probably something like that is probably it. Um, yeah. We have me and another collaborator, Junzi, had a unfinished draft where Junzi was doing all the theory of this method, but he got a job, and then I started Marimo, and so I never really saw the
Or
light of day.
or it might be kind of a 1.5 order retraction, sort of, since BFGS is not an honest
Yeah,
full Hessian thing.
yeah, exactly. Yeah. If you want to do the theory, I'd love to read it.
Uh, maybe you could, yeah, like Gumal or whatever, the Riemannian optimization guy. Give it to one of those gurus.
Yeah,
He's one like the man op developer,
yeah, yeah,
basically.
yeah,
He's the guy to do it. I'm
yeah.
just kind of have a vague notion of it. I'm not really an expert.
Awesome. I think it's a natural stopping point, but yeah, just wanted to say thank you so much, Akshay. I think it's been amazing to see the interest and the all the help that Marimo has been providing to researchers around the world. So yeah, and very excited to continue collaborating with you guys from our end.
Likewise, yeah, we're really excited to collaborate. Thank you for having us. One thing I forgot to mention is we are actively trying to help educators adopt Marimo. So if anyone wants help, we like literally go in and like we help like make Marimo notebooks for you. Like I'm I've been personally making notebooks for Zico Coulter's like a new modern AI course. You'll see these like Marimo links on his website. Um, it's fun for us. We want to see more educators using it. So if you are an educator, reach out to me, please, and or my team. You can find us on GitHub, Discord, wherever. Cool. Thank you.
Fantastic. Yeah, thank you everyone so much. I really appreciate all of you taking the time. And yeah, we have our next talk next week on evolutionary algorithms, which is a very new, interesting area of research with gradient free training. So yeah, we'll check out AlphaKive to stay up to date with the future talks. And yeah, thank you so much, Akshay, and everyone. Appreciate it.